Assalamu alaikum everyone. So today we will be having lecture number 32, and that is the last lecture of our course, that is Digital Logic Design with code EEE241, right? So we will be discussing data path analysis, right? So this is relevant to the last lecture, that is lecture number 31, where we discussed ALU, right? And in ALU we talked about two important components, right, or elements. These are the control and the data path, right? So these are the bullets, right? So we need to deal with the IOs, right, for certain interfacing, right? So if you talk about the computer, right, so you have different input and output ports, so you have to handle the data paths, right, regarding those IOs, right? So some data paths, they should be intelligent enough, right, in order to make certain decisions, right? So they need decision making capability, right? And then we need to move towards the software, right? So as we talked about the control implementation, right? So control is normally implemented as a series of instructions, and those instructions, they are actually software, right? Right. So here you can see that we have a diagram, right? So you can see this is the storage element, right? And this is again the storage element, and here we have the ALU, right? And these are the load registers, right? So here you can see that we can drive that wire, right, with the help of a tri-state buffer, right? So these are the tri-state buffers: in pass, out pass, and this is ALU pass, right? So if in pass is active, right, so this has to be inactive, right? So they cannot both be activated at the same time, right? So if this is activated, right, in pass must be inactive, right? So this is the requirement for the data path IO, right? So you can see whenever this is active, right, so we have data available and this is connected, so this storage element can float its data over this line, right? So if this is activated, so it means the data from ALU, right, it can be floated over here, or it can be passed, or it can be laid down over this line, right? Okay, so here you can see that two values enter from left, right, A and B, right? So you can see that if this is A, so in X I will be loading the A number, and in Y I will be loading the number B, right? So load X and load Y, right? So 4 steps, right? So we need to perform 4 steps over here. First we will be performing A plus B plus A, right? So these two has to be added, right? And then we again will be adding the resultant with A, right? And then in, right, X, right? So load A, right? So load B. So here we have to load A, load B, A plus B, right? So A plus B, right? So the resultant has to be stored here, right? So you can see that we have to perform A plus B plus A, right? So resultant has to be stored here, and then A plus B plus A, and this is out, right? So here you can see that this is out, right? So whenever we want to take the output, so this has to be moved here. This is again storage element, right? So we need to perform 1, 2, 3, 4 steps, right, in order to perform this, right? Okay, so as we all know that computer can understand only ones and zeros, right? So those instructions which we people can understand, they are meaningless for the computer or for the different control units or maybe the data paths and so on and so forth, right? So what we need to do, we need to generate the corresponding instructions in shape of ones and zeros, right? So here you can see that we have defined different states, right? So this is the ultimate goal is to perform this operation, right? So we have defined different states. Whenever we are at state 0, 0, loading has to be done in A. State 0, 1, loading has to be done in B, right? So if we go back, loading has to be done over here. 1, 0, right? So we will be performing the addition, and now the ALU will come into action, right? And addition will be performed, and the resultant has to be stored here in Y, right? And then we are at state 1, 1, right? So again we have to add, because this is the resultant, right? That is lying at Y, so Y has to be added with A, right? So Y has to be added with X, in other words, right? So here you can see that we have the state table, right? So this is the present state, right? And this is the next state, and this is the function, right? Load X, load Y, in pass, ALU pass, and out pass, right? So whenever I have to load X, right? So this is the present state and this is the next state, right? So you can see that load X, right, in pass is 0, is 1, right? So it has to be activated, right? So it is 1. So it means whatever is present here, it has to be moved here, right? And ultimately has to be loaded here, right? And then whenever we have to load Y, right? So in pass is 1, right? So it means the second number has to be loaded here, right? Right? So next second number has to be loaded here, and we again has in pass 1, right? So here you can see that we have load Y, and then again here 1, 0, right? So you can see we have to perform the addition, right? So again loading has to be performed, right? So now you can see that ALU pass has to be activated, right? So ALU pass has to be activated, and we are storing this here, right? And finally this is present state 1, 1, and we are again moving towards the this state 0, 0 state, right? And this is the function, and this is load, right? So there is no loading, right? So only we have to make the ALU pass, right, 1, and out pass 1, right? So we will be having all the information out, right? So whatever the resultant is, we will be having this. So if I place this, right, so you can see this is 0, 0, 0, 1, 1, 0, and 1, 1, right? So you can see we have 0, 1, 0, 0, right? So 1, 0, 1, right? And then we have 0, 0, right? So if I count this, right? So 0, 1, right? 2, 5, and 5, 2, 3, 4, 5, 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if we talk about the ROM, right? So this whole word is a full instruction, right, to all the units, right? So if you go back, right, so to all the units, right, so they will take or understand, right, whatever is instructions are present within that data for them, right? So next state function, right? So load has to be 1, right? So it's 0, in pass is 1, right? These are zeros, right? So each bit position or combinations of different bits, they are different instructions for different units, different paths, right? So similarly we have this next, right? So we have total 4 set of instructions within that ROM, right? And these are the 0, 0, 0, 1, 1, 0, 1, 1, right? So 4 different locations, and this is the present state, and this is the next state, and you can say this is the state storage element, right? So that can store the state, right? So now we have a more complicated example, right? So you can see that, right? So we have A plus B, right? Dot A minus B, right? So it means what we need to do, we need to compute this, and this has to be stored somewhere else, right? And then we have to perform this, right? And then we have to, so what we need the storage element, right? So for that, what we can do, we can add the RAM component, right? So this cannot be accommodated by using this configuration, right? So what we need to do, we need to add a RAM to the data path, right? So here comes the RAM, right? So you can have the size of RAM accordingly, right? So this is address, this is for read write, and here you can see that over this data path we have the RAM, right? So now we can perform this, right? So this can be computed and stored there, and then we can compute this and store here, and then we can AND them all, right? So here is the, so first what we need to do, right? We are going to perform this operation, right? So this is subtraction, addition, and then this is the ANDing, right? So first load A, right? So 0, 0, 0, right? So remember that previous we have 2 bits for state, here we have 3 bits for state, right? Because now we have to perform more number of operations, right? Before, here we have to perform 4 steps, 1, 2, 3, 4, right? So here 1, 2, 3, 4, 5, 6, right? So you cannot accommodate 6 operations by using 2 bits, right? So we need an extra bit in order to maintain the state, right? So here load A, right? So you can see load A, and then load B, right? So this is another state, 0, 0, 1, right? So this is present state, and this is next state, present state and next state, right? And then we have to add, right? And this, the resultant has to be stored in RAM, right? This is state 0, 1, 0, and then we will be performing subtraction, right? And resultant is stored at X, right? And the content of the RAM from the location where the resultant of A and B is stored, that has to be loaded, right? So we need 1, 0, 0, right? So this is 1, 0, 0, and next state is we are actually performing AND operation, right? So here we have the AND operation, right? And you can see A plus B dot A minus B, and the data is out, right? So now you can see present state, next state, and this is function, right? And this is load X, load Y, in pass, ALU pass, out pass, nice, address, read write, because now you can see that we have our RAM over here, right? So we need to mention address, right, and read write, right? So this is the address and this is the read write, right? So here you can see that RAM, the contents are stored at 4, right, and this is the instruction, right, read. We now have to read, right. So here on 100, right, so where is 100, right. So the RAM is written, right, on 100, right. So RAM is read, right, because this is sort of, so here we are reading, right. So this is the state, right. So here you can see that we have 010, 010, right, we are writing, right, and here for 100, right, so that is 100, we are actually reading, right. So this is the address, right. So I mention the state wrongly because this is the address, right. So now we have implemented the control ROM, right. So here you can say that we have the data and the control all together, right. So this is a very critical question, right. So the value of data matter, right, obviously yes, right, A to itself until overflow occurs, right. So here we are adding A to itself until overflow occurs, right. So there is no indication that an overflow has already been occurred, right. Here you can see that one value enter from the left, right. So if I go back, so this is left, one value enter from the left and add A to itself until overflow occurs, right. So now we are going to add A to itself unless overflow occurs, right. So xy load AB, right, state 0, next state 1, right, x plus y out, right, x state 1, next state if no overflow, 0 if overflow, right, 1 if no overflow and 0 if overflow, right. So this is a sort of active low. So what we need to do, we need to mention an overflow, right. So you can see that we have an overflow in the ROM, right. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right. So we have 14, and what we need to do, we have included an overflow bit in the RAM input, right. So we have included an overflow bit over here. So here we have implemented the control ROM with conditions, right. So as we know that the control path, it can have many inputs, right. So here we have overflow, carry out, 0, right. So we can use right, those control paths in order to have conditional operations, right. Okay, so here what we have done over here, we have replaced the control with the RAM, right. So in the previous example we have ROM, right. So here we have the RAM, right. So here we have ROM, right. Here we have ROM, and this is again ROM, right, ROM, and here we have RAM, right. So we need to read two values for RAM, right, from location 0 and location 1 and store to location 2, right. So this is a very normal operation, right. So we will be generating the address, corresponding address, right, and then we will have the read operation, right. We will have a control here for reading, right, and then after, right, location 1, 0 and 1 are read, right, then store it to location number 2, right? So perform memory read and writes, right? So RAM 0, this is location 0 and it has been loaded into X. RAM location 1, it is loaded at Y, right? So addition of X plus Y and the resultant is stored at RAM location 2012, right? So this is the state table. You can say that present state, next state, function, loading, right? So all the instructions and bits are available here, right? So this is the processor construction kit, right? So you can see that we have data path and we have the control path, right? So here we have different units, ALU, right? And this is for carries, right? And here we have the RAM, and this is the multiplexer, and here for the control we have ROM, right? So this is a sort of construction kit, right? And whenever we talk about the processor, right, so we talk about the compiler, right? So normally what are the steps, right? We write the C code, right, and the compiler translate that code into the assembly language, right, and assembly or assembler, right, that converts that assembly code to binary format in numbers, that these are binary numbers, ones and zeros, right? So this is the C program, right? For example, some functions may this is the declaration of integers, and this is the operation, right? And the compiler compiles this C code and generate the assembly language, right? Assembly program, and this is load R1, right? So this is similar to this one, right? Load A and B, right? Addition and so on and so forth, right? So these are the same sort of instructions, but the problem with computer is that it cannot understand this assembly language, right? So it can only understand zeros and ones, right? So ultimately the assembler, it convert that code to the binary format, right? And then it has executed, right, barely on the native processor, right? So that's all for first part of the lecture, right? So we discussed data path analysis, right? So data paths, they are very important component of the computer system, right? Whenever we talk about the I/O, right? So we need to manipulate or handle those data paths in an effective way, right? So we also discussed about the interaction between control and data paths, right? So that we can have an idea regarding the execution time, right? And then we have introduced ROM, right? And in one of the example, and after that we have replaced this ROM with RAM, right? And finally we also discussed that how we can have a full instruction, right, for all the components and units within the computer system or within the processor, right, so that they can have or they can understand the pieces of those bits, right, and bytes, and perform the functionality accordingly, right? So that's all for the first part of the lecture, right? So in the next part we will be discussing, right, or we will be having a recap what we have studied after the combinational logic, right? Because when we started our course, we first discussed number system, and then we talked about the complements, and after that we talked about Boolean logic, Boolean algebra, and then we discussed different laws and axioms, and after that we studied different simplification methodologies, right, how we can simplify, and then we discuss combinational circuit analysis and combinational circuit design, right, and after that we have a recap till combinational circuit design or combinational logic, right. So after that we started sequential logic, right, and sequential circuitry, and now today we have finished almost all the sequential part, and now after sequential part we discuss different designs and different processes and different analysis that are based on the sequential logic, sequential design, right. So we started from the point that why we need sequential logic, right, because we have this combinational logic, right. So the problem is that within the combinational logic, right, so there's no storage element, right, no timing is involved. So if we want to store the resultant, right, so there's no place, no option, no dimension that we can have the previous state of the circuit, right, stored at some place, right. So after the introduction of the sequential logic or sequential circuitry, we have an additional dimension, that is time, right. So in combinational logic the output is available as long as the input is present, right. So you can say that output is a function of input only, right. But as opposed to the combinational logic, in sequential circuit, right, the output depends on the current state, right, and sometimes it depends on the current state and the input, right. So it means sequential logic, it open more dimensions for us, right. So we can have more powerful tools, right, or more powerful methodologies and mechanisms for circuit design and circuit analysis, right. So we can have the independence of modeling, right, that cannot be accommodated by the combinational logic, right. So that's these are the justifications that why we need the sequential logic. And then we talked about sequential circuits, right. The basic building blocks of sequential logic, they are based on the fundamental Boolean algebra, right, and the building blocks are the fundamental elements. These are and or not, right. So the only difference is that we have the feedback, right. For example, if we have this is the NAND, right, this is another NAND, right. So what we can have the feedback, right. So this is a sort of feedback, right. So this is the input, right. So this is Q and Q bar, right, S and R. So you can see that these are the same elements which we use when we discuss combinational logic, right. So sequential circuits or sequential elements or components, they are based on the basic building blocks and or not, right. The only difference is this feedback, right. You can see this feedback. So we first started the sequential components by discussing latches, right. So the latches, they are level sensitive, right. So they are only able to recognize the level, right. So if we want to have the edge sensitivity, right, so the latches are not the right choice, right. So we after the latches, right, so we can have latches that can be made from NAND, NOR, and or inverter, right. And then we have SR latch, right, D latch, right, and the problem with SR latch is that we have certain race conditions, right, and we want to avoid those race conditions because they actually violate the fundamental and basic principles and laws of the Boolean algebra, right. So as you know that if we have a latch, right, over here, right, and other and NAND gate, right, so here I will be having this, right, S, R, Q and Q bar, right. So we have a we normally say that they are always opposite to each other, if 1 here and 0 here, right, 0 here, 1 here, but we have a condition where we have 0 0 or 1 1, right. So this is not true, right. So this is set and this is reset, right. So in order to avoid that sort of race condition, we introduced another latch, that is D latch, right, and D stands for data, right. So now we have avoided that race condition, right. And then we talked about flip-flops, right, and this is actually the most fundamental sequential component, right, one of the most fundamental sequential component, right, and it can store 1 bit, right, and the main difference is that flip-flop is edge triggered, right. So on the arrival of the active clock edge, it will perform the functionality for whatever it is designed, right. And as we know that we can store 1 bit, right, so we can bundle different flip-flops in order to have the more storage capability, right. So and we can also have the asynchronous input, right, for clear and preset. If you want to clear all the data that is stored inside those flip-flops, what we need to do, we need to clear all, right. So then we can also preset the flip-flop, right, and this is what I discussed, right. So combinational versus sequential. In combinational, output is a function of input only, right. So we don't have any state information, we cannot store, there is no storage element that is required for combinational logic implementation, right. On the other side, or on the other hand, in sequential logic, output is a function of present state sometimes, right. It is a function of output is a function of present state and input, right. So we need to take care of the state information. So in order to store that state information, we need memory, right. Examples are flip-flops, right. Then we talked about synchronous and asynchronous, right. So synchronous sequential logic, all the elements are clocked, right. On the arrival of the active clock, all the circuitry, sequential circuitry will function, right. So for example, we have flip-flops, right, and those flip-flops, they are using the same clock, right. So it means we have a synchronous sequential logic implementation, right. So in asynchronous sequential logic, it don't have any clock, right, and the state can change state at any point in time. It's faster, right, because we don't have to wait for the clock, right, but it's more complicated to design. So there is a trade-off, right. So asynchronous is faster, but more complications are involved regarding the design, right. And then we discussed registers, right. So whenever we talk about the flip-flops, right, so we can bundle different flip-flops in order to have a register, right. So a register is a combination of flip-flop, as each flip-flop can store 1 bit, right. So if we have a 4-bit register, so we need to cascade 4 flip-flops, right. So this is the definition of the register, right? And we can also have the shift register, right? If we have a shift left register, right, so we will be moving data towards left hand side, right? And if we have a shift right register, we will be moving data towards the right hand side. We can also have registers that can load data in a parallel way, right? So we have to provide the input, right, and all the data has to be stored in a single clock, right? So shift register application, it includes adders, right, and we can also use shift register in order to build the arithmetic units, right? Okay. And then we talked about counters because they are very important element within the computers, right? So we can have count up and count down, right? And that is decrement or incremental, right? So we have two different types of counters: ripple counter, that is asynchronous counter, and synchronous counter. In ripple counter, right, we provide clock at the first flip-flop, right? So rest of the flip-flop got clock, right, from the output of the next flip-flop, right? And in asynchronous counters, all the flip-flops, they utilize the same clock, right? So these are the two main types of counters. We have discussed another sort of counter, that is the Johnson counter, and we have a feedback from the last flip-flop. We have a feedback for the first flip-flop, right? Okay, and then we also have a binary counter, right? So it can count depending upon the number of flip-flops used, right? So if we have 3 flip-flops, right, so that counter can count, right? For example, 3 flip-flop, right? So it can count from 0, 0, 0, 0, 0, 1, 0, 1, 0, right? 0, 1, 1, right? 1, 0, 0, 1, 0, 1, right? 1, 1, 0, and 1, 1, 1, right? So it can count starting from 0 to 7, right? So the application of those counters, it involves watches, clocks, right, alarms, and we can also use those counters on web browsers or web pages, right? And then we talked about timing analysis, right? Because whenever we apply the input, right, it is not available at the output instantaneously. We have to wait, right? So this waiting time is normally called the propagation time, right? So whenever the input is propagated to the output, so we call it the propagation delay. Then we talked about the contaminational delay, that is when we apply input, right, and there is a certain time span where the output start changing, right? So it has not changed totally, right? So that time span is called the contaminational delay, right? And then we define the setup time and hold time, and we also perform certain analysis, right, so that we can design a clock by taking into account all those different parameters, right? So this is very important, right, for the analysis of the clock, right? And this is regarding the timing analysis, right? So we need to, the ultimate goal is we need to find out the maximum clock frequency, right? Whenever we talk about the sequential computer system or circuitry, right? So for the propagation delay, we normally take into account the longest path, right? So as this propagation delay is additive, but as far as the contaminational delay is concerned, we are looking actually the shortest path, right? So this is not additive or non-additive, right? So the ultimate goal is to design or to have an idea of the requirement of the clock, right? And then we talked about different memory elements, right? So we started from RAM, random access memory. So actually this is a collection of different storage cells, right? So we have also talked about the inside configuration or inside design of the RAM, right? So we have sequence of signals in order to access the data, right? And as we have different locations, right, that are available within the RAM, right? So in order to access those locations, right, so we need to generate different addresses, right? So in order to generate addresses, we have used decoders, right, that are the key element within those memories, right? So those decoders, they select specific data location within the RAM, and whatever operation we have to perform, read or write, so we perform that operation accordingly, right? So decoders are used in order to generate the address, right? So then we moved to ROM, right? So normally this is considered as read-only memory, right? But we talked about certain mechanisms that are used in order to write onto the ROMs, right? But we have to take care, because there can be some serious problems whenever we have some power outages or some problems like that, right? So the internal structure of the ROM is similar to the SRAM, right? And actually the ROMs are the implementation of the truth tables, right? So if we have a Boolean function, so what we can do, we can draw the truth table from that Boolean function, or if we have a truth table, we can also have the Boolean function, right? So we in the combinational logic, whenever we talk about the combinational design and combinational analysis, we discuss the try-can, right? So how we can move from circuitry through the Boolean function, and then from Boolean function to the truth table, right? So as we know that truth table represent the unique representation, right? So it is a unique representation of any Boolean function. But on the other side, if you have a truth table, you can have a lot of different Boolean functional implementation, and similarly we can also have a lot of different circuit implementation, but the truth table has to be unique, right? So that's why we call that ROMs are actually the implementation of the truth tables, right? So if you have a truth table, you can implement that truth table by using ROMs, right? So then we also discussed about the ROM utilization for the implementation of finite state machine, right? So we can have different implementation, as we know that we can have melee machine and moire machine. In moire machine, the output is a function of the present state only, right? In melee machine, output is a function of present state and the input only, right? So we can implement those state machines, or we can use ROMs whenever we are implementing those different state machines, right? So the ROMs, right, they are actually constructed or designed with the help of diodes, transistors, and FETs, right? And then we talked about the size of the ROM, right, and how we calculate the size, right? So this is the same, right? ROMs, here we have the truth table, you can say addresses and data, right? And then we talked about the effective implementation of ROM, right? So the problem with the ROM, that for ROM we need the combinational circuitry and decoder, right? So decoder is used in order to generate the min terms, right? So the problem is that if we have 3 bits for addressing, right, and it will generate 8 different min terms, right? So there can be certain scenarios where we are not using all those different min terms, right? So we need some sort of intelligence, or we need some sort of programming. So in order to have some simplification, right, or minimization, we introduced programmable logic arrays, right? So we can have efficient implementation, right, by using PLAs, right? So these are actually, we can program, right, and we can avoid the min terms which are not being used, right? And finally, we talked about ALU, right? So that is arithmetic logic unit, right? So this is actually the main computation unit within the computer system, right? So it can perform different arithmetic and logical operations, for example, and, or, right, not. These are the logical operations, right? And we can also have different arithmetic operations, that is addition and subtraction, right? So then we talked about an ALUIC, right? So it has certain limits, right? So for example, it can manipulate 4 bits, right? So we can have a number of 4-bit only, right? So if we want to have the addition of a big number, right, for example 8-bit number, right, so what we need to extend the ALU, right? So we have proposed or introduced the extension of ALU, that how we can concatenate or we can cascade different ALUs in order to extend the length of the number that has to be manipulated or that has to be handled whenever we are applying different operations, right? So we can extend the ALU, right? And then we talked about different data paths and control paths, because whenever you talk about the ALU, right, so we 2 key components are very handy, right? First one is the data path and the second one is the control path, right? So we talked about the data path and the control path, right? So and then we have certain examples, right? And we started from the code or the instructions that are readable by human beings, right? So these instructions or states, they are not understandable by computer, right? So then we converted those different statements, right, by using the state table, right, into the ones and zeros, right, so that the units, the components that are being involved whenever we want to perform a certain operation, right? So the each unit and the component, it can understand its own bunch of bits and pieces, right? So we have shown the implementation of RAM and ROM when we talk about the combination of data path and the control path, right? And finally, we talked about the problem that whenever we have an idea regarding the digital logic circuit design, what we can do, we can draw the specification, right, the requirements and the required functionality, right, and then what we can do, we can have the circuitry, right, after performing or after the knowledge which we have learned so far on a piece of paper, right? But if you want to verify that either it's working or you want to perform some analysis on the basis of all different inputs which you can provide, right, So for that you have to go to the lab, right? So especially for remote learning, right, this sort of facility is not available all the time, right? So in order to overcome that shortcoming or difficulty, what you can have, we can have a software, a simulator that can do the job, right? So what we can do, we can design, right, on paper, right, and then implement by using that simulator within the computer, over the computer, and then we can simulate and analyze, right? So we discussed a tool, Circuit Maker 2000, that can be used in order to plot the circuit, in order to design the circuit, in order to have the analysis sort of thing, right? So that's all for this course, not for this lecture. So we have finished 32 lectures, right? So I hope that you have enjoyed this course, right? And I have good wishes for you, right? And good luck for all of you, right? So I hope you will be using the material, right? And you will be going through different course materials, handouts, and you will be studying the textbook, right? And I have mentioned my email address, right? And my contact information, right? At the start of this course. So if you have any problem, you can reach me at my email address, right? So that's all. So hope to see you again. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम.